Hello everyone, in this lecture we'll talk about some properties of the determinant. So the most important that determinant is always for the square matrix. We can't compute the determinant for matrix that isn't square. So always for the square matrix with n by n rows and n columns. So they must be equal. So the square matrix. And the determinant for a triangular matrix. So triangular matrix is any diagonal or upper triangular or lower triangular matrix that we have seen before. So all this matrix called triangular matrix, and their determinant, it is easy to get it, so it is always the product of the main diagonal. If we have, for example, 3 by 3 diagonal matrix A1 1 0 0 0 A2 2 0 and 0 0 A3 3. So the determinant of this matrix, the determinant of this matrix is equals the product of this main diagonal. So A1 1 A2 2 and A3 3. And also if we have, for example, any element here, so upper triangle, for example, matrix here, for example, can be any, for example, B different of 0, and here, for example, C. And even if we have this, the determinants stay the same here, A1 1 A2 2. So it's always the main diagonal. And even if we have, for example, here B and here C, which is a lower triangular matrix, so it will be always the same. And the determinant for the identity matrix, which is the diagonal matrix with ones here, for example, I3, for example, is equals the determinant of I3. Let me write it here. The det of I3 is equals that of 1 0 0 0 1 0 and 0 0 1, which is equals 1 always. So because 1 times 1 times 1, which is 1. And if we have a matrix with row of zeros or column of zeros, so always this matrix, the determinant is always equal to 0. For example, if we have a matrix A, B, C, 0, 0, 0, D, E, F, so its determinant is always equal to 0 because it has a row of zeros. Or if we have, for example, here zeros and here 0, and here, for example, C and here F, for example, so if we have this row of zeros, so that means that this matrix is determinant is always 0. And the same here if we have two proportional rows or two proportional columns. For example, if we have a matrix 1 2 3 and 2 4 6 and 5 7 8, so this matrix here, when we look to this row and this row, we can so name it here, for example, row 1 and row 2. So row 2 is equals to row 1 because when we multiply here by 2 we'll get 2, when we multiply by 2 we'll get 4, when we multiply here by 2 we'll get 6. So these two rows are proportional, and that means that the determinant of such a matrix is always equals 0. And it is also for the two proportional columns. So if we have matrix with two proportional columns, like for example 1 3 4 and 5 6 7 and for example 3 9 12, so these two columns here and this one here and this one are proportional. For example, this column here C3, for example, and C1, let's call this C2, for example. So this C3 is equals 3 C1 because here when we multiply by 3, so 3 will get this, and times here 3, which is 9, and times here 3 is 12. So this kind of matrix has always, or this kind of matrices have always determinant equals 0. And also the determinant of a matrix A is always equals the determinant of its transpose. For example, if we have a matrix A and have a transpose matrix A transpose, so that's the determinant of this matrix and the determinant of this matrix are always equals. So they are always equals. And the determinant of product of two matrices AB is equals the product of the determinant of each of these matrices. And the determinant of scalar multiplication of a matrix is equals that scalar power n, which is n here. This matrix here is n by n, for example. So this k power this n times the determinant of A. For example, if we have a matrix 2 by 2, for example, 2 by 2 matrix, so it will be Ka, Kb, Kc, and Kd. So this is the equals k square of A, B, C, D. But this when this k is multiplied by each entry of this matrix. However, if it's, for example, K, A, and Kb is just for one row, so here C and D, this equals k of A, B, C, D. So isn't square, there isn't power n. When we have a square that multiplies just one row of matrix, we can take it outside the determinant, but won't be power anything. However, if it is multiply each entry of this matrix or each entry of this determinant, so we can take it out and it will be power the number of rows or the number of columns, which is here equal, so times the determinant of this matrix. And we have defined that a matrix is invertible if it has A minus 1, another matrix that's the product of A minus 1 gives the identity matrix. And we can say also that it is invertible if the determinant of A is different from 0. So if you have determinant of A different from 0, we can say that this matrix is invertible. However, if it is equals 0, we say that this matrix is not invertible. And the determinant of the invertible matrix of A minus 1, is equals the inverse of the determinant of A. So this is how we can get the determinant of an inverse matrix of A.